Okay, in this video I want to talk about how we can use the linearizations for the functions f and g that we found in the previous slide at the point 1 minus 1, how we can use these linearizations to identify whether this equilibrium is stable or unstable. So we started with this system of nonlinear first order differential equations. And in fact, the differential equation dy dt, that was linear, but the equation for dx dt was not. And so what we can do is then rewrite this entire system, which was with regards to x and y, in terms of our new variables u and v. And so just recall that u was defined as x minus x0. So you can almost think about this as like a small change in the x direction away from the x coordinate of the equilibrium. And so if I take the derivative of that equation with respect to time on both sides, then I get that du dt is equal to dx dt minus 0, since x0 is 0. So in other words, du dt and dx dt are the same. So I can take dx dt and replace it with du dt because we have this relation over here. And then we took the function f of x and we said, okay, we're only interested in what's happening in a really small neighborhood around the equilibrium 1 minus 1. And so if we're zoomed in really close to 1 minus 1, which is what we want to look at when we think about stability, we're just thinking about solutions that start close to the equilibrium. Do they stay close to the equilibrium? So if I'm only looking at values of the function really close to the equilibrium, then I can approximate 1 minus x squared at 1 minus 1 with the corresponding linearization minus 2y that we found. And then we also linearized g, which was already linear, and we got the equation minus 3u minus 3v. So here's our linearized system. So we would call this the linearized system. And so now if I want to think about what is the stability of the equilibrium at 1 minus 1, well, here we've got ourselves a good old linear system of first order differential equations with constant coefficients. So I have du dt, dv dt, and those are equal to, and now we can write this out as a matrix equation in the following way. So the top equation, we had minus 2 in front of u, and we have no v's. And for the second equation, we have minus 3u and minus 3v. And if we want to think about whether this equilibrium is stable or unstable, then we can find the eigenvalues for the corresponding matrix. So just remember, we would want to find the characteristic equation of this matrix by setting the determinant of the matrix when we subtract this scalar lambda from the diagonal entries equal to 0. And so this determinant would give us minus 2 minus lambda, minus 3 minus lambda, and then the product of the off-diagonal entries is 0. So here we've got two distinct real eigenvalues. One of them is minus 2, one of them is minus 3. And so when we have two distinct real eigenvalues and they both happen to be negative, then this is going to give us a stable a stable sink. Okay, meaning that at the point 1 minus 1, we've got a couple of negative eigenvalues. So I don't know what the eigenvectors are, but maybe they look like this and like this. And what we can see is that in this case, everything should be heading in towards that equilibrium. It's very stable. Keep in mind that here this analysis only applies to what's going on around the point 1 minus 1. And if we were to try and consider what's going on at some other points that are far away from that equilibrium, this analysis isn't going to tell us that, because these approximations are not going to be appropriate for points that are far away. But when we're talking about stability, we're really just talking about if we start off really close to the equilibrium, are we going to stay close to that equilibrium? And here we can see that yes, we're not only going to stay close to the equilibrium, as time goes on, we're going to get closer and closer and closer and head back towards that equilibrium. So 1 minus 1 is definitely a stable equilibrium.